Assalamualaikum, a very good day to our lecturer Dr. Zahra bin Ahmad and everyone watching. We are from class F4CDCS 3050C. Today our group will present our project title Automated Skin Tone Classification via Learning and Computer Vision. My name is NURUL and RAHEEM. To begin with, let's look why this project is necessary. We know skin tone identification is highly subjective and 10 ecosystem due to variation in room lighting, camera qualification, and human bias. In industry like e-commerce, such as when consumer is trying to find the right makeup foundation online, users frequently struggle to find the exact shade, leading to incorrect purchase and product mismatch. Furthermore, the current digital solution commonly fail to isolate skin pixels from detailed background or shadows, which severely compromise qualification accuracy. To address this issue, our project outlined three main objectives. First, to develop a pre-processing pipeline using computer vision technique to detect faces and extract poor skin color regions. Second, to train and evaluate deep learning classification model to accurately classify skin tone according to the Monk skin tone or MST scale. And thirdly, to develop a lightweight, web-based prototype application that enables user to upload image and reaches immediate skin tone classification. Okay, looking to our project scope, we specifically target static digital fashion image. By using MediaPart 5 mesh, our system isolates skin color from stable fashion regions such as cheek and forehead to eliminate non-skin elements such as hair and clothing. We then implement color normalization to reduce lighting variation. This holds great significance because it directly addresses the subjective of skin tone assessment across cosmetic and dermatology. By using computer vision to isolate skin pixel and deep learning for classification, we reduce human bias and improve shade matching. Furthermore, utilizing the Monk skin tone scale support diversity while lightweight implementation provide practical, efficient, and scalable method for regular customer device. Next, I'll pass to AFIFAH to break down our system architecture.
Thank you, Alia. Assalamualaikum and a very good day to Dr. Zabah and everyone watching. My name is NURUL OSMAN and I will be guiding you through the system architecture, core data engineering pipeline, and a live demonstration of our functional prototype. As illustrated in our block diagram, the proposed solution operates as a synchronized three-tier framework: the UI ingestion layer, the computer vision pre-processing layer, and the deep learning inference layer. This structured flow ensures that raw and predictable real-world facial images are systematically cleaned, filtered, and standardized before ever reaching our neural network model. Let's look at the first phase, the UI ingestion layer. Built entirely using the Streamlit framework, this layer serves as a direct user gateway. To maximize usability, we engineered an intuitive interface that accepts inputs through dual ingestion streams. Users can either drop a static image file or capture a live frame directly using a webcam snapshot stream. To elevate the production quality and professionalism of our software, we bypassed the default dark theme. We injected custom CSS styling to implement a fresh, high-contrast, bright aesthetic layout. This design choice utilizes clean white container cards, a soft slate grey canvas background, and sharp typography. This significantly enhances the user experience and ensures the application is highly readable across different display monitors. Once an image is received, the system captures the data array and we utilize the OpenCV library to instantly decode it into a native BGR pixel tensor. Next, the tensor moves into our computer vision pre-processing layer. Passing a raw and edited portrait directly into a deep learning model introduces a massive amount of environmental noise. Variables like clothing, background furniture, hair textures, or ear accessories act as a distracting artifacts that degrade classification performance. To enforce high data integrity, our script initializes MediaPart face mesh. The algorithm instantly tracks detailed 3D facial geometry. Our custom pipeline isolates the stable dermal structures across three specific regions of interest: the forehead, the left cheek, and the right cheek. The system automatically masks out all peripheral data to pure black and stitches these clean dermal segments together into a single isolated skin patch. However, isolating the skin is only half the battle. Real-world environments introduce unpredictable ambient lighting variations that alter the color presentation on camera lenses. To overcome this, our pre-processing pipeline transforms consolidated skin patch from the traditional BJR color space into the CIE-LAB color space. This step is mathematically vital because it completely decouples light intensity from actual color pigment details. The L channel isolates raw lightness while the A and B channels retain pure chromatic contrast. Finally, the patch is rescaled via bilinear interpolation to a standardized resolution of 128 times 128 pixels, and we reverse the channel ordering to account for TensorFlow's JPEG loading behaviors. This creates a clean illumination invariant input tensor ready for neural evaluation. Now, let us walk through a live demonstration of our functional prototype. As you can see, the interface is bright, structured, and user-friendly. To demonstrate the system industrial robustness, let's look at our automated exception handling layer first. In a real-world deployment, users might accidentally upload invalid images or experience severe underexposure. Watch what happens on screen when an image without a clear human face is uploaded, or if the webcam view is completely obstructed. Instead of crashing with a Python execution error, the system intercepts the pipeline. It renders a clean, vibrant red error alert notifying the user that face detection failed. Underneath, it dynamically displays a troubleshooting guide instructing the user to check their frame alignment, avoid harsh background lighting, and clear away any facial obstructions like thick hair, bangs, or masks. This keeps the application running smoothly and guides the user effectively. Now, let us restore the system by providing a valid image source. The moment a proper face is captured, the system seamlessly recovers. On the left column, you see the raw target captured, and on the right column, you see the live output of the pre-processing tool. A cleanly cropped isolated dermal patch completely stripped of background noise. Finally, the tensor is shaped into a 4-dimensional matrix and fed into our deep learning engine. The network computes the classification matrix and outputs a clean diagnostic at dashboard displaying the predicted skin tone group along with the precise pipeline confidence threshold. This fluid transition proves our software architecture is reliable, fast, and commercially viable. That concludes the technical implementation and demonstration phase. I will now hand the presentation over to ALYSYA to analyze our neural network configuration and experimental findings.
Assalamualaikum and a very good day to Dr. Zabba bin Ahmad and everyone watching. My name is ALEEYA binti HEZRIE. Moving to our core machine learning architecture, our system utilizes a custom 3-layer sequential convolutional neural network built on TensorFlow and Keras. To optimize training, we configure the environment with an ADAM optimizer for dynamic learning rate adjustments and use sparse categorical cross entropy as our loss function. Our dataset distribution use a strict 18/20 split. 18% for robust model training and 20% reverse for independent validation on entirely unseen data. Our experimental setup evaluated a refined subset of the skin tone 100 dataset, totaling 199 high resolution pre-processed image. To test foundational classification boundaries cleanly, the sample is evenly split, containing 100 dark and 99 light category image. While our code is engineered to handle a 4-tier system including mid-dark and mid-light, our current experimental baseline focus on these two populated subsets to ensure statistical balance. Our network's learning behavior over 50 epochs is shown here. On the left, training accuracy started at 53.46% in epoch 1 and sharply accelerated to 96.23% by epoch 50, with validation accuracy stabilizing beautifully at 97.50%. On the right, the loss curve collapsed from 1.0479 down to a new 0.0916. The minimal gap between the training and validation curves mathematically proves excellent generalization with zero overfitting. Testing on our validation subset yield a dominant overall accuracy of 97.15%. Notably, we achieved a perfect recall of 1.00 for the dark category, meaning 0 missed dark samples, and a perfect precision of 1.00 for the light category. The single misclassification in the confusion matrix was caused by heavy ambient shadows along the cheek boundaries, which slightly skewed the calculated luminance values. In conclusion, this project proves that a hybrid pipeline combining media pipe geometric masking with illumination invariant CIE LAB color space conversion achieved top-tier computer vision performance. Pre-cleaning background noise allow our lightweight CNN to hit 97.50% accuracy using fewer than 200 image. Moving forward, we aim to populate our intermediate data directories to expand this system into a full 4-tier multi-class classifier. That's all from me. Thank you very much.